Good evening, everyone. Thank you for taking time for today's workshop. Let me start very quickly on about ourselves and a quick agenda for today's workshop. My name is Vinay, and I'm the CEO and founder for Arya.ai. Explainable AI has been taking a lot of attention in the recent times, while AI adoption is increasing, and while we see more use cases where AI is being used as the core driver, the end user or the primary builder themselves, both of them, are now seeing the importance of having a transparency in the system. It's not just from a regulation standpoint, but also from a fundamental model building standpoint as well. If I can able to understand how the model is functioning and how it is working, I could probably find ways to improve the model. Whereas from a user standpoint, user needs to have the confidence on the system that can be built by giving them a clear understanding on how the model is working and what would be the scope boundaries for the model. So hence, you could see a lot of adoption or a lot of requests around explainable AI. So in the today's workshop, we'll introduce some of these concepts, and we'll also do a hands-on implementation of Arya-xAI API for image classification use case. To start with, today both me and Shashwat will be in today's workshop. As I introduced myself, I'm CEO and founder for Arya.ai. My research has been around deep learning in my college as part of my master thesis. When I was doing my research, I was using deep learning to predict remaining useful life for turbine engines. This is way back in 2012, 2013, when I was completing my research in IIT Bombay. So at that point of time, deep learning was fairly new. So we were more excited to use deep learning before looking to understand how it works. But the excitement is pretty much shared across the community even today as well. And along with me, I have Shashwat. Shashwat is our head of R&D. He had been working on deep learning for almost 7.5 years now, and he heads all the research and development efforts at Arya.ai. He also had authored an open source framework called Braid. It's a meta framework very similar to Keras that we published in 2015. And he heads all development efforts for Backtrace and xAI offerings at Arya.ai. So we will be the primary speakers for the conversation today. And for the agenda, so we'll be starting off with quickly introducing what Arya does and introducing explainable AI. And Shashwat will talk about what are the current methods that are being used specifically for deep learning. And then we will introduce what Arya-xAI is and the rationale behind building Arya-xAI and comparing it with other current methods. Post that, we will do a hands-on implementation of Arya-xAI API for the image classification use case. So we are planning to finish this within 45-50 minutes, and then we'll have another 10-15 minutes for the Q&As. So let me start very quickly about Arya.ai. We are an AI PaaS, AI platform as a service for financial institutions to help them deploy fully autonomous AI systems using deep learning. So deep learning is very core to us, and we have been building products around deep learning in financial institutions for the past 7 years now. So Arya started in 2013 from Mumbai. Currently, we are a team of close to 25 people. So we have 70-80% of the team being researchers who had past experience either from acads or hands-on implementation in the industry. So we are also funded by a couple of VC funds, UNS and Sparkle Fund. So being one of the early players, we had an opportunity to present and talk about our findings and our implementations across multiple forums across the world. So we were active participants in multiple global deep learning conferences like NVIDIA GTC conference or Zephyrs conference in Hong Kong and so on. So having said that, we also work with multiple partners because to be able to truly democratize deep learning and AI, we had to work with multiple partners in the ecosystem and thereby enable the ecosystem itself. So we are part of Intel's AI Builders program, and then we are also part of NVIDIA's Inception program as well. So we had a chance to work with them closely and work with the improvements that are happening in the industry. And from a adoption standpoint, currently we work with multiple financial institutions in Asia, primarily in India and Southeast Asia, because of being close to these markets. All in all, on the platform today, we process close to $35 billion worth of transactions. Total transactional value is around $35 billion on the platform today. So the problem that we're trying to solve is simplified deep learning, primarily for financial institutions. We understood that deep learning works really well if it is used properly. And when there is enough data sets, which is primarily most of the use cases in financial services are qualified to use deep learning. But the problem with deep learning is it's really complex. It takes a lot of research efforts and a lot of efforts to build a new architectures in deep learning, which means that most of the problems or use cases that you see in financial services are yet to be deployed using deep learning because most of the current deep learning use cases are driven by an open source community where datasets are public, where neural networks are public. They are easily used to customize and build products around it. For example, if most of the current largely commercially adopted use cases are around image classification, language modeling, which for most of the base for that is already is an open source networks. When it comes to financial services, as the datasets are private, which means that research is also yet to take a full position there. So while deep learning can deliver, the biggest problem with deep learning is on the explainability and traceability, because these are very complex algorithms. So it takes a lot of efforts to build and a lot more efforts to explain the systems. And having AI transparency becoming a legal norm as well. For example, in the European Union, close to June, July of this year, there is more clearer legal framework around AI explainability and AI usage. And financial services is one of the most regulated industries, which means that they have to have the explainability and transparency as the fundamental part of the product, but to be able to use at a large scale. And thirdly, most of the tools that are available today around deep learning are horizontal tools. So they address a general purpose use cases. When it comes to deploying them in financial services, you require to make a lot of customizations, which means that you also need skill set not only on the model building, but also system setup, scalability, maintenance, and so on. So, which actually makes it really expensive process and very, very long process as well. So these are the typical challenges that you would see when it comes to adopting deep learning in financial services. So that's a problem that we are trying to simplify and solve by providing a modular stack and offering plug and play kind of modules, such that if a user in financial services can pick up the module that they want and customize it by providing training data. Or if it is already pre-trained, they can use it as is as well. So hence you could see multiple modules which are business functions in a financial services process. You could see them as a plug and play API or customizable modules. So on the platform today, you could divide the propositions into 3 different classes. One is AI APIs, which are plug and play kind of modules. And then second class is AI experts, which are designed for core functions, core decision functions like underwriting function, fraud detection, audit, or transactional fraud, and so on. So, which are customizable for a business by providing training data. And third is explainability. So as it is a fundamental requirement, so we are offering our LOCO framework as an independent framework, but also along with our core products as well. So the intention is we want to achieve to a stage where we can offer all business functions in financial services as plug and play API functions. As we are using deep learning exhaustively, one of the common requirements is explainability. So we have seen this problem very early on when we started productionizing the deep learning in financial institutions. So in a financial services vertical, you have multiple stakeholders, multiple class of stakeholders who needs to validate the product before it can be used in production. So this class of stakeholders starts with the business owners, as in the user who is using the solution. For example, in financial services, that could be an underwriter or a risk manager or a sales expert or even an actuary, for example. So these guys needs to have a comfort that the product is serving their purpose and it's serving it rightly. So they need to validate that the product is working and it's accurate, and they are confident on how the system is functioning on those use cases. So they have a lot of questions on how does it work, or how can they trust the AI system? How did it arrive at that verdict? So these are the common questions that we would see when we are deploying AI. And then you have risk managers in financial services. They play a very critical role in defining whether an AI solution can be productionized or not, because eventually these are the guys who manage or monitor the risk in the business. So their questions will be around not just from system performance, but also system fairness perspective as well. Like, is there any bias? Are there any foreseen circumstances of undue fairness to certain class of users because the data was defined like that? So they would have a lot of questions on how the system is working, questions around fairness, questions around regulator compliance, and so on. And then audit and regulators will have questions around tracking the progress and consistency in the system as well. The biggest risk of any solution is it working 100% while productionizing and working at 50% accuracy when the production rollout has started, which means that they'll have a lot of predefined risk metrics when it is productionized. If it is not consistently maintaining it, then they do not have a consistent risk function, which is again a high risky proposition. So they tend to not to have solutions like that, where there is no consistent risk risk defined from the solution. And end customers, as these are financial transactions, they would have the right to know the reason for the transaction. For example, let's say as part of underwriting, the system is predicting that not to issue or not to accept. Then the customer has the right to understand why their case is not accepted. So these are the common questions that you would see when you deploy AI in financial services. In fact, if you extrapolate these questions and pick up any vertical, not just financial services, you could pick up a healthcare use case or a retail use case or a manufacturing use case. The questions are very similar. How can I trust it? Is it consistent? Is it working in the manner as per the expectations? So these are very common questions on using an AI solution. So these are the questions an XAI framework can address. Now, how can we deliver this, right? You could do this as an ad hoc exercise, as an like you could have a data science team who could spend, let's say, a couple of weeks or a week's time to analyze the decisions and give them the evidences from the data, saying that 80% of the times the decision was acceptable because of these reasons. That's what model has learned, and so on. But again, these are ad hoc efforts, as in you may have to do this from time to time, and you may have to do this for case to case. But that may not give 100% confidence to the user, right? If somebody has to spend time and effort to create evidences, then it all depends upon the person who is generating the evidence and also when it is being generated. So instead of that, the expectation is to have this evidences in hand in real time or in near real time, such that they would have this evidences or explanations in place, and they can use these explanations wherever is required. So that can be done only when you have a plug and play and a full framework. So that's where an explainable framework can help you to adapt explainability as part of the design instead of looking at it as a separate ad hoc kind of process. And it's really important actually. So it goes to a very fundamental question, like accuracy is a fact, but not an evidence to the performance. When I say it, for example, your model could be very accurate, but until unless you understand what is happening behind the hood, you you yourself may not be confident that the model is working fine. Because, for example, you can take this a very common example that is used whenever somebody talks about explainability is an image classification problem, where in this case the model is built to predict between a husk and a wolf. While the accuracy is more than 96%, 97%, but when you actually do the explainability around it and understand what model is learning, so in most of the cases, it is actually learning the snow as one of the key important feature to predict a husk. So that's not right? You would actually need to understand what features are going into the system as part of the learning as well. And you could see the result as the backlash, or as a negative feedback to the AI ecosystem itself. Like there are a ton of articles that was published talking about the bias in the model, or categorizing humans as gorillas. So you could see that happening in many use cases in the recent times. So it's better to understand that before you even productionize the solution, until instead of receiving this feedback from the public, from the press, or even from the regulator. So this is what explainability as a framework will help you to have the accountability, trust, and transparency. It can help the data science team to find more and better ways to prune the model, and it can help you to create new controls as well. So having said this, now let's look at how can we achieve this, right? Or how is it being done today, and where does Arya come into play? So you could see this as a common graph where the dimensions is between accuracy and explainability. But again, this is debatable to some extent, because in some use cases, even though neural networks are supposed to get better accuracy, maybe a classic ML can deliver better accuracy. But again, let's keep that aside. But there is a commonality between the complexity of the model and complexity of explanations. The more complex is the model, the more tough it is to explain the model. And the neural networks are definitely one class of models where they are really tough to explain deep learning. So as I think so far I have introduced what the problem is, what's happening in deep learning. Now let's look at what's happening. In fact, to explain this, I'll ask Shashwat to take over and talk about what's happening in deep learning, explainability, and Arya-xAI, and also the workshop as well. Over to you, Shashwat.
Thanks, Vinu, for introduction. In this course of next few minutes, we'll go over what are the existing methods, what is being prevalently used, and then the motivations behind creating a new algorithm. And post that, we'll go over how to use the platform and how you can analyze results from our API. So to start with, current methods can be categorized into visualization-based methods and distillation methods. Visualization-based methods highlight parts of your data which are strongly influential towards your output. Okay, so they can either do this by considering the network structure or using different components within the network itself. For example, activation functions or convolution maps, feature maps, and gradients to propagate back what input was responsible for that particular output. And then we have perturbation-based methods. These methods treat the network as a black box, as a complete black box. These methods try to remove or alter information to see what are the changes in your network output, and based on those changes, they can either highlight, okay, this change was affecting more, or calculate marginal contributions based on each part of data. So it can be a different feature in case of tabular, or a word in case of text. In case of images, there can be parts of images, or it can be as few as a couple of pixels. So these are visualization based methods. In case of distillation methods, these methods build a white box model with in conjunction with your current model. Okay, so you have a trained deep neural network. Distillation methods will build a separate model to explain this, so that white box model will have a simpler complexity. Okay, it will be less complex, and it should be able to explain what is happening within the network. So how do they do that? So there are two methods: local approximation and model translation. So in case of local approximation, the methods use a small range of data, small data set, which is concentrated around some particular score, to approximate the behavior of the neural network. And within that range, they explain what should be the reason, or which inputs were more responsible for that particular score. So it's analogous to how Taylor expansion works. Taylor expansions tries to convert any complex nonlinear function into a linear function. So this is a similar method where you're building a simpler white box model on top of your complex model, but on a smaller range. But in case of model translation, you use your complete data to try to map your input to your network predictions, not the actual target, but not the ground truth, but the predictions, so that you can map with a white box model the input to prediction, and using that white box model, explain how their decisions are being made. So you're not exactly using the your original model to explain results. You are using a surrogate model in this case. So these are the various methods which come under different categories. So in case of backpropagation methods, where you use the network structure, we have activation maximization, deconvolution, class activation maps. So these utilize your either the pooling layers or the convolution layers, the activation functions, to propagate backwards what feature maps are being more useful for the prediction. So these actually heavily rely on convolution layers to be present in your network. Okay, and then we have layer-wise relevance propagation, which uses Taylor expansion in a similar way to propagate relevance from your output towards your input layers. Deep lift and integrated gradients use a reference sample to calculate what was the impact based on the change between those two. So the deep lift directly takes those differences based on different components of the network. Integrated gradients, they that method integrates the complete path, the gradient along the complete path from output to input between your sample and your reference, to calculate what was the influence of this particular feature in your output. And this can be both positive or negative. So many of these methods give both a positive and a negative influence. In perturbation based methods, it's a similar. We remove parts of the occurrence sensitivity, you erase parts of the image. This is mostly image based. In differentiation eraser, you can it's similar, but it's more data agnostic. You can apply this for any kind of data. In case of text, you'll remove words. In case of tabular features, you'll remove or a single feature. And in case of images, you can erase parts of images. And that erasure is can be in any form. You can either replace it by constant values or average values, or there are multiple methods, but essentially you're altering the input to see how the output is being affected. So this requires multiple iterations of the model. Multiple times you have to run the model to get one explanation. Okay, and SHAP is quite prevalent. I think most people should be familiar with SHAP. Um, so this comes from Shapley values, which comes from game theory. So Shapley, so this considers marginal contribution from every feature. Okay, so marginal contribution in case of tree-based methods is easier to calculate because you have an ordering of features, and based on that ordering, you can go through that order. Okay, you can there you have depth-wise ordering also and feature-wise ordering also. So you can consider different orderings, different types of removal within the same sample. Okay, you can remove, you can see average values of every node before being forked. Okay, so in case of tree-based method, this works on a single sample, but this ordering or depth-wise order doesn't exist in deep learning as such. So in deep learning, how SHAP works is you take a data set, a sample data set, and from there, the values for each feature is permuted to see how much that particular feature uh, can is affecting your output. Okay, and that marginal contribution will be your explanation for that particular feature. Local approximation, you make a surrogate model on a small data set. Lime is useful for that. It generally uses a random forest, but you can also use any particular algorithm for in Lime. And model translation. So in model translation, you're building a simpler model. So you can have a tree, you can have a full system automaton or a graph or even rule based. So basically, if you have a completed neural network or a huge step neural network, each node you can try to convert into a rule, and that will try to explain how your model works. So basically, but this has its own caveats because now you're converting a continuous system into a discrete system. So it has its own caveats. Uh, so these are existing methods. There are a lot of methods which cater to different use cases. So why something new? So we have while going through these algorithms, right, for the various deployments which we have, uh, we find a few shortcomings with them. So the first one, this also went into the thought process which should go in when designing a new algorithm. So the first one was it should work independent of network architecture. So some of the algorithms above, they are heavily dependent on what component you are using. That should not be a case. I mean, we should be able to define any architecture and get explanations on that. It should not be the other way around. That based on what algorithm for explanation I'm going to use, I'm going to define architecture. That should not be the case. Then second is the output should be based on only the model and input data. We should not use a separate reference sample or a sample set. We have the model and sample in hand, so we should be able to explain how that particular sample was being used inside the network. We should not require a second set of data or a data sample to explain that. Third is in case of data types, so they should be should be applicable to any data type. Okay, the new algorithm should be able to work with textual data or image data or text data, or in case of tabular, you can have a mix of all three, and it should be able to handle all of them. And lastly, you should get an explanation for each part of the network. So providing explanations is only part of the reason why these algorithms are used, right? Another part is you should be able to understand how your network is working, what is it seeing, so you should be able to make improvements. So if you have explanation on each part of your network, you can uh, uh, quantify each change you're doing in the neural network. It won't be subjective. You can quantify what change you're doing, how you're fine tuning, what parts you want to prove. In case you want to alter data, which features have very less influence, which have more, so you can have a different weights for each of them, different weightage while going in, and you can also see if those weights are compliant with your business process. So essentially, each neural network is built to automate some process, and in our case, since we're working in financial services, it's built to replicate a financial process. In case of financial process, the financial process depends on the data, and in that data also there's a different ordering of each feature, right? Means some features are more important, some features are less important than others to make a decision or to for an outcome. That same ordering should be reflected in the model also. Then only we can uh, then only people can assume, right, that your model is able to directly replicate this particular business process. Okay, so this helps in that. So moving on to, so these were the motivations for that. Okay, so along these ideas we built a new algorithm. So what was the starting point? So for starting point, we used the most basic structure we had, that was a fully connected perceptron model basically. So in case perceptron model, you can see you have one layer below, layer X, which is connected to layer Y. Each node is connected to every other node on the above layer. Okay, and it's defined by this basic equation, Y equals to your activation function over your weight matrix into your input layer plus bias. Okay, and you can have any dimensions here. So our thought process was that since every node is connected to every node below, right? So the node which is contributing upwards, I should have both kinds of influence, first of all, both positive and negative. So most of the algorithms above which we saw only give you a positive or a negative influence for every feature. But in case of deep learning, that's not exactly true, since every node is contributing to every node above. So this is true for any kind of layer basically. In case of convolution, one kernel operations is similar to this, or one pooling operation is similar to this. In case of recurrent networks, one gate operation is similar to this. So since every node in the every unit in that is contributing to every node above, so there should be both influences uh, allocated to the node which is connected to your output node, or in case your below node, the node below is connected to everything above. So in case the above 5 nodes had someone had positive, some had negative, the nodes in the X layer should be able to reflect that. Okay, and that was a starting point, and based on that we wrote the initial algorithm, that how this progression should happen, and then we scaled it up for to reflect the functionality of each layer type, is commonly used in different neural networks, and we'll still expanding that to cover more and more layer types. So how, so that was the operation which happens. So how this converted for complete network. So in the complete network, we do first do a forward pass from your input to output. Once your network output has come, the entire output is assigned some weightage based on what is the scope of the use case and what is expected from the explanation. So currently, we are automatically assigning for classifications and regression cases. Uh, we also have a functionality where a user can provide their own maps. Currently, we're not providing this with API, which we plan this to in future. Currently, it's undergoing testing. So in future, should be able to assign your own weight map any way you like. So this will be essential in case more complex outputs are there. For example, augmented segmentation, where part of image can have similar weightage, right? So once this assignment happens, along with this weights which is attributed to the output and the layer outputs, each layer output, we assign weights to relevance weights to each layer, and this operation keeps on going until all the input layers are populated with relevance weights. Okay, and the algorithm stops once all inputs are populated. We handle multiple inputs, so that's not an issue. You can use tabular data, you can use multiple images also in same uh, network, and all of these will be assigned relevance weights based on your output. Okay, next. So how does it compare to existing algorithms? So we have done this table based on the use cases and the data types. So like I said above, our goal was to make it data agnostic, data type agnostic. So it is data type agnostic. You can use any kind of data, tabular, text, images, category features, or combination of all of them to feed data into the network, and the algorithm works for it. Currently, it's both functions for both classification and aggregation use cases, and you also don't require any separate data set, separate sample, or a surrogate model to explain. Just that sample is enough to get explanations. Okay. Now coming on to API. So that was the algorithm part of the system. So while offering this an API, we try to make it as user friendly as possible. So when you start using this as an API, you will uh, get the relevance feeds for input layers. So you can multi-unit dimensions are preserved in those as these are propagated backwards from your output. Uh, then since we are not using any proxy model or something, that is exactly the output you're going to see for your model. So if you feed the same data again and again, you're going to exactly see the same explanation again and again, because you're not relying on something else. So if you feed some data today and maybe an year from now, if there's an audit, you feed the same data again, you're again going to see the same explanation. So there won't be any change in that. And then inner functioning also you can analyze. So currently in API, we are providing the ways for input layers, but once we offer customization on that, uh, you should be able to get output for all the layers of your network. So in case you want to use this string training or data engineering, then you can use outputs from all the layers to fine tune a network or tune your network, or fine tune your data also. You can remove features based on which is having more influence, which is having less influence. Okay, and we provide both positive and negative influences. Now, some of the limitations which currently exist in the API itself. So these are limitations of the API currently. So the API is currently limited to classification and regression use cases. So the algorithm handles all. So, but for offering this as an API, we're currently limiting it to classification and regression use cases. Further down the line, we'll open it for other use cases also. Currently, it's limited to single output models. So you can use multiple inputs, but output should be a single layer. And finally, execution time depends on network architecture. So since it's extremely compute heavy, uh, depending on what kind of layers you're using, what kind of components are being included in the network, it can be depending on how much compute is required for each component, your execution time will vary. So for example, our current layer is extremely parameter heavy, but it's not compute heavy. Okay, it goes sequentially, but each computation happens only once for each cell. But in case of say convolution layer, it's very light in terms of parameters, but it's extremely compute heavy. So same kernel
Shashwat, so we can't hear you.
and finally what we are going to what data are going to see today. So today in for showcasing our API, we are using ResNet 50 network architecture. So it's a 49 convolution layer deep network. Okay, and in total it has 177 layers. It's pre-trained on softmax, and it's pre-trained on ImageNet data using softmax, and this is 1000 class data. So we try to use a pre-trained model for this, so that this example we are showing should showcase what a general usage should be for any user. Okay, so this is the
Shashwat, we can hear you. Ketki, are you able to hear
should
Shashwat?
be applicable for any network out there. So moving on to the platform. So this is the xai.arya.ai platform. Here, once I think we have provided credentials for all the participants here, and once you log in, you can see a My Models option here. So once you into My Models, so I have already uploaded some models. So you can add a model. So you'll have two options: saved model and H5. So H5 is S5 format, which is the Keras format for model, and saved model is the TensorFlow model saving format. So you can use either of them to upload a model. The URL should be downloadable by the system, so it should be a downloadable link. So when you enter those, it will once you press submit, we'll download the model. We'll load the model and test out if it's working with the system. If it's all good, fine. Then you'll get back to the listing page. So in case of in listing page, you'll see your model token. This is a unique token associated with each model you're uploading, model type, and when was it uploaded. Okay, and here you can go and see the documentation for API, how to use the API. So this is the URL to follow. It's a post. It's going to be a post request. The API token for that particular model. This API token is going to change for each model. So you have to make sure that you're using the correct token for the model you're going to send data to. And then in the request body, you have these parameters. So the mode is default contrast. So in case of default mode, uh, we only give positive inferences back. It's a single inference algorithm, so it's based on numerical contribution. Okay, so based on which class was maximized during a prediction, we'll provide the input map for which features in your input was had more contribution towards your prediction, essentially. In case of contrast, we get both a positive and a negative matrix for influence. Token is a model token, is multi-input, is a flag, true and false flag. So in case your model has multiple input channels or multiple input layers if you're using, then this should be true. In case of single input, this should be false. Model input is same as what you feed into the model. It should be converted into a list and attached here. Okay. Now this model input should not contain batch dimensions. So when I'll show you an example of how API request is made, the batch dimension, I'll show the batch dimension should not exist in this. Scalar is uh, it's a floating point number. It goes from 0 to above to any number, and we made this feature available to make users should be able to compare between different samples, right? So in case scalar, you don't provide scalar, right? How propagation will happen, how weight allocation will happen is based on the score. In case of say classification, based on the score which your maximum class is having, the score will be multiplied by 100, and that will be propagated backwards. So say the score for your class is 0.7. So the weight assignment will be 70, and that 70 will be propagated backwards. If you want to scale this to any number, you can provide a scalar here. So if I provide a scalar value of 1, then that 0.7 will be scaled to 1, and then that 1 will multiply to 100. So now 100 will be propagated backwards. So in case you want to compare different samples, the output of xi between different samples, or you want to average them for a more uh, global explanation, then you need to keep the scaling same, so that same weight is propagated backwards for each of them, right? So you can use the same scaling for all of them. And one example, you can use any scaling method. So we multiplied by 100 inside, so you can also use 0.01, so that will bring down your output weight to 1. So here you need to make sure that based on your input map, you're providing uh, enough magnitude as such. Okay, because for example, if your input map was large, this same number is going to get distributed. So for we are going to use ImageNet. ImageNet is 200 by 200, 224 by 224 by 3 channels. So that kind of feature map, that is 150,000 pixels. Okay, so if your value, if you make the final weightage as 1, right, that 1 is going to get distributed among those 150,000 pixels. So the difference between weightage between into different pixels will be very less. So use this depending scale your weightage depending on uh, what is the size of your input map. Okay, and prediction is a flag, true and false flag. This is meant for network output. So in case you're integrating directly into your current system and you don't have a specific method for hosting, you can directly use this system to get both the predictions of your model and the XI output also. So if this is true, this predictions is true, then you will get the network output as part of the response. In case this is false, if you're already using some method for hosting, if you're using TF serving, then you can remove this part. We won't send predictions back, so that will decrease any overhead on the bandwidth you're using. But in case you want to avoid hosting on Orient, then please use this. So when you send the request, you'll get this response back. Okay, so in case of contrast mode, you will have data. This is a fixed key. Inside, you will have name of your input layer. This name is extracted from the network itself. So the name of the layer which is defined inside your network, we are going to use the same name here. And here you get a positive and a negative uh, key and weight matrix, which will have same dimensions as your input map. And this can have multiple keys based on how many input layers you have. Okay. And network output, in case you want predictions, then this will be the name of your output layer as per your network. And similarly, the prediction. Okay. And in case you don't want predictions, then you can pass false, and this will be an empty dictionary. So you will still get this key, network output. So your API won't break. Just inside will be empty. And in case of default mode, since we don't have a positive or negative influence, you will have the Arya-xAI output directly attached to your layer name, and network output will be the same. So this is the API format. So moving on to actual usage, how to integrate in, how to script for this and how to use these. So here I'm using a simpler model. It's built on MNIST to showcase how how to change different fields in the request and what kind of response you're expecting. So these are some help from functions to first print the output structure and to normalize weights for plotting. So data I'm using is for digit 3, it's MNIST data. So here I'm printing the shape of the input. So as I said, there should not be any batch dimension when you're sending. We assign batch dimension from our end when we run the model for XAI. So in case you were passing this to model, there would have been a separate dimension in the beginning to account for batch. So that should not be there. So this should be as same as what raw data looks like. And then coming on to the API request. Okay, so in API request, this is the URL. I'm using this particular model. Token for this is this. And In contrast mode, there is only one single input, so multi-input is false. Scaling is 1 currently, and predictions are false. So I don't need predictions currently. So I can run this. Okay. Uh, okay. Yeah, I can run this and response. So this is your output response. Let's go to this. So success is a Boolean flag. So in case it's successful, if we don't face any errors, the success will be true, otherwise it will be false. So this can uh, help you evaluate if the request was successful or not. Data, as we seen earlier, data contains their name, input layer name. So it is this in this scenario in the network, a positive and negative flag in case of contrast mode. Inside there is a list because JSON, and then the shape of that is 21, 28, 28 by 1. This same as your input map. So the shape of the explanation is exactly same as what should be your input map, and same for both positive and negative. There's no batch dimension in this. And network output is currently empty because I pass predictions as false. So in case predictions is true, okay, and we'll change the mode to default to see the other response also. We'll run this, and here you'll see that we don't have positive negative anymore. Same name of the input layer, and here you have only one input map sent back because it's just positive influence. And in network map, you'll see there's one more key here now. That is your name of your output layer according to the network, and the shape of this is 1 by 10. So here you will get the batch dimension, and we are sending this because that's the way how model returns, and that's how people have integrated with the models. They expect batch dimension, so we are also sending it back batch dimension in the network output. So 1 by 10 because as this is MNIST, there are 10 classes, so you're getting 1 by 10 output. So this is how you use API, how different responses work, how to change different fields for different responses. Now we can move on to the ResNet and ImageNet data. Okay, so here again similar imports. Okay, helper functions. So there are a little more helper functions here. Print JSON is for simply printing the response format. For processing the image, we didn't have any extensive processing done in this, no major pipeline, because this should represent what how people use the network, right? What data is going to be sent to us, and how model is going to be evaluated when we get a model which we don't know what data is going in. So we use pre-built functions in case we are, in this case, we are importing the function directly from Keras. So we are not writing any processing steps from our end. This is same as, so in case you get this model directly from Keras, these steps are exactly same what you do there. So no additional steps are required to run XAI. And then there is a function for XAI itself, the request function, similar same fields here. Mode, I'm passing mode and skill and prediction, I'm passing through arguments here because we'll be seeing different responses for all of them. Then these functions, one is for normalizing the output for plotting. So the network weights which you see can be extremely small in magnitude. So to plot them, we have to scale them back to cover the whatever color map you're using. So this is for this function is for that. And then the difference function to get the difference and get an absolute value for the positive and negative parts of the difference, to separately plot them, how positive and negative weights are behaving. So currently we're going to use three different images. So currently we're going to consider these three samples. So these three samples chosen to highlight how different types of objects and how different foreground and background arrangements will work for explanations. So the first sample is of a fox. So there you can see the object size is small, but the patterns are very similar between foreground and background. Even the color scheme is quite same. In case of second image, the bisected one, uh, the object takes a much larger fraction of the image, and also it is not homogeneous, it's heterogeneous, and it's not uniform. The object is not uniform. And then third sample, the object covers a much larger fraction, but the object itself is uniform, and there is quite some difference between patterns of the object and the background. Okay, and here's the model. ResNet 50. So the input shape is 224 by 224 by 3 RGB input, and the output is 1,000 classes. So when you go down here, this is the name of the input output layer predictions, and the shape is 1,000. So coming down to default mode. In default mode, we set that we will only get one response, okay, for each sample. Okay, so here's the response structure. This is the name of the input layer, and one list attached to it, and the shape of that list is same as input by 224 by 224 by 3. Okay, and since predictions for true, you'll get the predictions back. So there are 1,000 classes, so you're getting 1 by 1,000 back. So coming to output plots, these are how outputs look. Okay, so since we are normalizing them, the pixels you see are the most influent, and you see most of the background has turned to black because they are not contributing much to the prediction. So this is purely based on numerical contribution. So only those parts are being highlighted which are contributing significantly towards your prediction. Okay, and this plot is RGB. We have scaled the output from xi between 0 to 1 to show how the image looks. The output looks essentially. So the outputs for all three images. Then moving on to contrast mode. In contrast mode, as we discussed, we are going to see both a positive and a negative weight matrix. So here you'll see in the response, you see a positive weight matrix and a negative weight matrix, both same shape, and the output matrix. So in this case, as you see, there is quite some difference between those and these two, the positive image and the negative one. There would be a difference in magnitude also, since we are normalizing them separately. We see similar color scheme in both. Both are being normalized to 0 to 1, but you can normalize them together also to see a more coherent picture map in case you want to plot them together. Uh, so different parts are being highlighted separately. So as I explained earlier, each pixel should have both influences. So each pixel also has both influences here. So there are some places in the background, as you see, which has more negative influence, and then positive ones also have some negative influence because same pixels are also contributing to other classes also. But there is a difference between both outputs, the positive and negative ones. It's more prevalent here, where there was a stark difference between foreground, background, and the patterns in case of the castle image. Okay, so this was contrast mode, and these are the images without normalization. So as I said, the value of the maximum value of the weight matrix is very small because we are distributing a very small amount. In our case, it's 100. We scale to 1 over 150,000 pixels. Okay, 150,000 values, basically 3 channels, 50,000 pixels each. So when you start plotting them, it's so close to black. Directly plotting doesn't show us anything. So we decided to scale them to actually see how the image looks like, how the distribution looks like. Okay. Now coming to the scaled mode. So here in contrast mode above, there was no scaling, and the scalar was zero or none. Here scalar is one. Okay, so both are separately being the scale to one, and then the backtest runs on them. The response structure is same. There is some difference in this. So these images look similar to what above only because of plotting them separately. But when you try to take a difference between the positive and a negative sample, then you will start seeing differences between the outputs. So here we are plotting the difference. So we took the difference because for taking difference, they have to be on same scale. Otherwise, it's not representative of what the image is doing. That's why you have to first scale them. That's why a separate run was done for them with scalar one. So since both are on same scale now, we took the difference and then we plotted the positive part separately and negative part separately. So this is positive minus negative output from xi, and then the middle plot represents the positive part of the difference, and the last plot represents the negative part of the difference. So you'll see where the positive influence was more and where the negative influence was more. These plots highlight those. So they still follow the same object structure, is if you can see that. And there are parts of the object also which also contribute negatively, which I think contribute more towards the other classes. Okay, so that you can see here by taking direct difference in scale mode. So this is just the explanations part. Okay, that you can directly use. This is how your data is being used, and this is how explanation looks like. Now, how to validate those and us to use them further, to use them further, we have. So first, will try taking statistics of both positive and negative components. Okay. So this is from the scale mode, contrast scale mode. Okay. So for the gray fox one, so for complete 150,000 values, 50,000 values per channel, we ran statistics, and these are the values for that. So as I said, the maximum value for any pixel is very small. It's 0.03 in this scenario. That's why we are not seeing anything in the direct plotting the image itself. We have to scale them to actually see the image. But more importantly, you see there is a very high kurtosis value in this. So this represents a very high tailness. So why heavily tailed influence in this scenario? So the image, if you remember, the patterns are very similar between the object and the background, and even the color scheme is similar, and the object was uniform. So in this scenario, means what we expect is, because the object is uniform, there should be a peak because weight is going to be distributed uniformly across the object. But because the background is also very similar, has similar pattern, there should be a very heavy tailness. There'll be weights allocated to most of the background also. So that you see in the gray fox scenario. The kurtosis decreases for bicycle and the castle sample because the background was very different. Okay, and in case of bicycle, uh, the object is not uniform; it's very heterogeneous. So you should see a more rounded peak. The object should have a high weightage, but that weightage won't be uniform. So different values will be assigned to different parts of the object. And in case of castle, it's uniform, so you see a pointed peak because it's a uniform object. So when we try plotting the distribution of those components, you'll see the similar effect which I was describing earlier. In gray fox, you have a pointed peak because it's a uniform object, but there's a huge spread because the background is very so similar to your foreground, and it's very heavily tailed because of that also. So the first plot is for the positive component, second plot is for negative component. Uh, In case of bicycle, there's a more rounded peak. As the object was heterogeneous, the weight is uh, a lot more distributed across different parts of the object with different values rather than a single value. Okay, so these plots are a log scale because the weights for weights range from 0.03 to 10 power minus 8 in case of gray fox. So to uh, show how they represent in distribution, we apply log base 2 on them. Okay, and these are the direct values of those. Okay, so for the gray fox, the log values went from -25 to -4 for positive component. So that's what you're seeing here. Graph is goes from -25, the lower end of the weight matrix, to around -4. So the higher end on the weight matrix. And similarly for castle, you'll see there was a stark difference between the object and the background. So there was the spread is less, but there is a peak also upon peak because the object itself was uniform. So similar weightage will be assigned. So since weight values will be same, almost same across, so for that value there'll be a huge peak. So that's what we are seeing here. So this is just based on the distribution itself. This is before even seeing the plots. Okay, this was before even seeing the plots and how distribution works. Uh, how distribution works. Now we can move on to plotting the images, and you can also test explanations by removing parts of the images which we see it's relevant or not, and based on a fixed threshold. So the threshold I'm choosing, which I have plotted here, this green line represents the threshold I've chosen. I've chosen same threshold because uh, this is the most common exercise that anyone can do. Provide a threshold and then uh, add add or subtract data based on that threshold. You can have separate threshold for each channel and then plot them separately, so you can have more detailed analysis. So what this validation represents is the most common validation you can do for any data, any type of data. It's just not image data. So these plots will resemble same for a tablet data or a textual data in case of words. So how we test? So first we'll try switching off pixels which are low for both positive and negative weights. So we are testing for bicycle example, right? So this one. So in this, everything left to the green line, we are going to switch off in case of both plots. Okay, both for both positive and negative. Okay, so in total there were 149 non-zero pixels. The rest were blacks. Okay, 17,000 pixels had in positive component were below the threshold, and negative there were 15,000, and in total there are 21,000 taking union of both that were below that threshold. So how we did this was the original prediction. We removed those pixels by assigning them 0. Okay, in our case, so they won't affect the outcome, those pixels. And then we ran the model again. Okay, so when we ran the model again, you'll see the prediction hasn't changed. The score assigned to the class has decreased a bit, but the prediction hasn't changed because we picked those pixels from the lower end of the plots. Okay, and this is how the images looks after removing those pixels, those particular pixels. So then the left image you see is the original image, and the right one you see what is left after removing those pixels. So it has become a little darker because the pixels were removed from separate from each channel. So that's why image looks like this. Then we can move on to removing high positive and low negative components. Okay, so high positive, so everything right to the green line in positive and everything left to the green line in negative. So above we had 17,000 pixels, which are lower than threshold. Now we have 132,000, which are more than the threshold. So rest which are left from 114,000, 49,000, right? And in negative, it's same as above, 15,000, because we're using the same threshold. The overlap between those two is 4,000 between these two components, the above threshold and below threshold, the positive and negative components. And then after removing this 4,000 pixels, we again ran the model. So the model score decreased a bit because we removed a few of the pixels, right? These are not these are not many pixels, but these pixels were from the high positive area. So the model score decreased a bit. The prediction is still same because we're not removing many pixels, but since these were affecting the score in a positive way, your score decreased. Okay, and then we can do a reverse analysis of this also. We can remove high negative and low positive pixels also. So in this, what we did, we had 17,000 pixels, which are below the threshold in case of positive. And in case of negative, now we have 135 pixels, 135,000 pixels above the threshold. The overlap between these two is 6,730. So these pixels, 6,000 pixels, have a low positive impact but a high negative impact. Okay. So when you remove these, your score actually goes up because you are removing pixels which are affecting negatively more and positively less. Okay. So positively more and negatively less. So why this analysis is there? We can to test out predictions and distributions. You can use this in training itself. What kind of how for different object, how it's working, how it's not working, and how score works. Okay, and in case you want to improve your predictions, right, improve your model performance, how would it turn out? Okay, so you can use this type of analysis to study those if your explanations are working correctly or not. Okay, and why this type of analysis? I mean, could have directly removed the positive or negative part. So as we have seen the theme over the deck towards from the different notebooks, right? The influence every input will have, it can be both positive and negative because every component is almost connected to everything else in case of classification. So if you remove positive or negative directly, right, each pixel has both positive and negative influence. First of all, so effect can be arbitrary, and second, the positive component is only affecting one class. Okay, it's only it is only derived from the predicted class, but the negative is being derived from all the other classes. So the effect of removing a negative component is distributed across different classes, but positive is allocated only to the positive class. So even if for any pixel the positive value is less than negative value for that particular pixel, it can happen that your score decreases in spite of removing that pixel, because the decrease in score for other classes was comparatively less compared to what was supposed to be an increase here in your positive class. Okay, so uh, this brings us to the end of the XI demo. Uh, Now moving on to Q&A. If you have any questions, please feel free to ask. We'll answer them live or send you answers.
Yes, so Shastravit, thank you for the detailed presentation. We have some questions in the chat section. So if we could just take up those questions, it would be great.
Sure. Okay, so so the first question which someone asked is, what is the role of domain knowledge in explanation of DL models? Right. So, like I explained during while explaining the motivations behind backtrace, the each component is going to get different weightage, right? regardless of which algorithm you use. This is in general. And there's going to be some order. Then some features are going to get more going to assign more influence. Some are going to be assigned less influence. This ordering uh, should be representative of what the use case is representing, what that actual process is representing, and in that the domain knowledge comes into picture, right? So if you have the domain knowledge for that use case, you know whether which feature should be more important, okay, process wise, actual process wise, and then if that is getting reflected in the model itself, okay, for that you can use the explanations. And if that is not the case, then that model is not exactly representing your process, right? After that you can tweak the model that will and make it more aligned with your process also. So we made this algorithm specifically for that purpose, since we mostly work in financial processes. And financial processes, this is extremely important because the liability is so high that your aspirations should represent the actual business process, okay? And if it's not representing, you can always tweak so that it comes in alignment. The features, the managers think that should be more important, the domain experts think should be more important, should also get reflected in the model, okay? So that's how domain knowledge will help. And for any use case, this is important. Any use case, any explanation algorithm, and any model. Okay. Then moving on. So next question I'm gonna ask is, how does making the algorithm function independent of network architecture affect the issue of biasing and overfitting? Algorithm function independent network architecture. So this would affect I mean, this is mainly for algorithms which work independently. Our algorithm is heavily dependent on what is network architecture. So we are not affected by what kind of architecture is built, but we are directly going to use the architecture to derive the explanation. So in case the model is overfitted, it has a heavy bias. So this overfitting and heavy bias is also going to show up in your XAI output. So if you're overfitting over because of some data, then that data is going to get a larger part of the influence compared to your other data features. And it's similar for bias. If it's biased towards some data, then that data is going to get a bias less towards some data, then that will be similarly represented in your XAI output. Okay. So you can use the XAI output to study whether there is a bias or overfit towards some data, but it directly doesn't affect our algorithm. Then next question is, can backtrace also handle multimodal data at once? Yes, it can, like I explained before. So we kept the algorithm independent of data pipelines. Okay, what the algorithm expects is the data which is eventually going to be fed into the model. Okay, the data which is eventually encoded and passed through the complete data pipeline. So at that point, just before the model, it's completely numerical. At that point, different modality doesn't exist. Only numerical data exists. So we are dealing directly with that. So you can use any data you want. You can use textual, images, both of them together. It won't affect the functionality. You just have to pass that through your data pipeline, and whatever final encode data you have, which you're supposed to pass on the network, you can send that to us, and the algorithm will process it. The next question is, will it be able to explain why particular entity is recognized and from where in the text in the NLP entity recognition model? Yes, it can. The explanations you are getting are on unit level. So basically, if you feed word embeddings into that, you're going to get you're going to get values with of same dimension as your embedding itself. So for each bit in encoding, you're getting the relevance weight. Okay, so if you're using say a 300 dimension embedding for feeding into the model for each word or for sentence, then each of them will, each bit in that 300 dimension is going to get a weightage, and from there you can analyze which bit was affecting more, which was affecting less, and you can also and average out over different samples or different words to see which bit has the most effect over your recognition. And finally, we have how are explanations from backtrace helpful to assess data model drift. Okay, so this is easy actually. Since you are having a direct matrix output, you can directly plot them like I plotted them and do a direct distribution comparison. And in case you are comparing different data set, you can do a global explanation by using same scaling across, average them out, and then compare between data sets directly. You can directly compare distributions now. So in case you have different modalities also, so you can use any layer, because we have layer wise explanations, right? You can use any layer which is common across all modalities and then use that to compare. So if you are having multiple input streams, so you don't have to compare on the input streams end as well. You can use any layer in the middle, use the explanations for that for comparing distributions, and that will give you an idea regarding if data is drifting, or in case model drifting for same predictions. If you are getting a different distribution, then you'll know the model is drifting. Okay. I think that's the end of all the questions.
Yes, thank you, Shashwat, once again. And if we could just move to the last slide, we have shown the contact details.
Yes.
So thank you, everyone. That was the end of this webinar. We hope you got some additional insights about it. Now, these are the contact details for our team. So you can see Vinay's and Shashwat's contact details. Alternatively, if you want to reach out to the team, you can reach out to us at hello@Arya.ai. We would be available to answer any questions, or if you again want a one-on-one demo on the platform, we would be happy to do so. Thank you so much for taking our time for this webinar. Bye, everyone. Thank you.